All right. So let's begin here. So again, part two of the final review. So we're covering the latter half of this class. So first, before we even do the first problem, notice what I provide you here. What do we recognize this as here? This is Planck's constant, right? So this will be provided on the exam. Okay, the only constants you'll be given on the exam are Planck's constant and the gas constant. So, but everything else, like speed of light, Avogadro's number, you have to memorize as well as all the equations. So I'm giving this to you here for your reference, all right? So number one is a blank electromagnetic spectrum. So I'm saying for this blank electromagnetic spectrum, fill in all boxes with their appropriate waves from the given bank, then label the proper relationships between wavelength, frequency, and energy. So let's start first with labeling the different types of radiation that we have here. So let's start here with the middle. What type of radiation is here? Visible, good. All right, so visible light, this is the only portion, right? Notice how it's such a small sliver here, right? This is the only portion of the electromagnetic spectrum that we are able to detect without any, additional like instrumentation or anything like that. Right, so the visible, of course, this is our whole world, right? So now let's go towards the right. So what type of radiation is right next to visible with, and notice it's increasing wavelength. So what has longer wavelength? Good, this is going to be infrared. So IR. Okay, you guys have probably heard of infrared. That's like what's used like the night vision like goggles that like military and those people use. This is also what if you're chilling at home, like you're changing the channel on your TV, your remote uses IR radiation. All right, what's next here? Microwaves, right? And we definitely know about microwaves. Sure, we all have one. And what type of radiation has the longest wavelength? Radio waves, right? All right, how about going to the left? So what is just to the left from the visible portion? UV, good. And we definitely know about that here in Florida from the sun and getting sunburned. What is after UV here? X-rays, good. And what is the final one going to be here? Gamma, good. Okay. All right. This is annoying. So are we all good with this, the radiation here? Okay. So make sure we memorize that, right? We need to know the order, and we also need to know the relations in terms of wavelength, frequency, and energy. So let's quickly, I'm going to just rewrite this. Okay, so now for looking at the relations, right, we want to know about wavelength, frequency, and energy. So starting with the left side of the equation, right, and here we have an electromagnetic wave, right? How does wavelength, what's happening to the wavelength as you get further to the left? Good, it's getting shorter. Remember, the wavelength is the distance between two crests. So in other words, the distance between these two peaks here, right? That's not aligned, but you get the idea, right? That is wavelength. So if the wavelength gets shorter or smaller going to the left, what happens to the frequency? gets higher, right? So the frequency, right? Remember the definition of frequency is how many complete cycles are happening in a given amount of time, right? So you could see, right, these cycles are like more bunched up over here, right? So what do we know about the relation between frequency and energy? Not inverse, directly proportional. So if we have higher frequency, what's going to happen to the energy? It's going to be higher, right? I just said it accidentally. Okay, so this left side of the electromagnetic spectrum, this is like the dangerous side, right? High energy and why it's like dangerous to us, right? Notice how small these wavelengths are, right? These are like on a nano scale. So when the wavelength, of X-rays, gamma rays are so small, that's able to, penetrate into your body and go into like the DNA. And of course, like we hear all the time, like with UV, right? People, if you don't wear sunscreen, you're gonna get skin cancer, right? That's because these, radiation waves are going in and they're damaging the DNA. So now we go to the right side, okay? So what's happening to the wavelength as we go right across the electromagnetic spectrum? Good, so wavelength is getting longer. So then what happens to frequency? It's shorter or it's decreasing. And then what happens to the energy? It's going to decrease. So this side has the lowest or lower energy. Okay, so this is why the left side I said was dangerous. The right side is not so dangerous, right? Especially radio waves, right? We are from the moment you're born till the moment you die, you're being hit with radio waves, right? From radio stations, and even here in this room, we're using Wi-Fi, which uses radio waves. Same thing with Bluetooth, right? So any questions on this spectra here? Okay. All right, so let's go to number 2 now. So a radio station, WFAN, emits a frequency of 101.9 megahertz. What is the wavelength of these radio waves? So if you haven't done it already, I'll give you a moment to work through this, and we'll go over it in just a second here. Okay, so in this problem, I'm giving you the frequency of this radio station, and you need to figure out what the wavelength is. So what formula is relevant to solving that? So we know we're going to use C equals lambda times nu, right? So speed of light is equal to the wavelength times the frequency, and these are all together, times frequency. Okay, so what did you guys think to do first in this problem? Good, convert megahertz into hertz, right? Remember, when we're using this equation, all of these variables have to be in their SI unit. So we have to be in hertz for the frequency, right? So we have 101.9 megahertz We want to convert that into hertz. So 1 megahertz is 10 to the 6 hertz. Your megahertz cancel. You will get 1.019 times 10 to the 8 hertz, right? So now that we have nu in its proper unit, we can do our math, right? So what do we plug in for C in this equation? Good. So what was that again? What's this number represent? Speed of light, right? And it's a constant, it never changes, ever. So that is equal to lambda, which I'm solving for, times the frequency in hertz, things. So times lambda times this. Right? So how do we proceed from here? We're solving for lambda, right? So it's just some algebra from here. Solving for the unknown, we're going to divide both sides by our frequency. So this cancels off, right? If you're one of the people that like to rearrange the equation before doing it, that's fine. So what this is saying is that, the way you rearrange it is you would say that lambda is the speed of light divided by frequency, which is what I'm doing here, right? Speed of light over the frequency. So what do you guys get for lambda? 2.94. Anything else? Meters, good. Remember, units are important in chemistry. Okay. All right, any questions about that one? Okay. All right, so number 3 now says that a device emits light at 245 nanometers. What is the radiation's frequency? So same equation, right? But instead of solving for wavelength, now we're solving for the frequency. So first things first, you have to convert nanometers into meters, right? So when you do that, you multiply by 10 to the negative 9. So you're going to get 2.45 times 10 to the negative 7 meters. And then we just plug in. So speed of light is equal to wavelength in meters times frequency. Solve for frequency, you divide both sides here by your wavelength. And what is nu equal to? One 1.22 times 10 to the 15th. And whoa. Good. So I'll write the unit down here because I'm out of space. But remember, there are 3 acceptable units for frequency, right? We use hertz, which is the most common. We can also use 1 over seconds, or you can use inverse seconds. Right, and the whole reason why we have that unit of seconds, remember the definition of frequency, it's how many complete cycles are occurring in that amount of time. So specifically, we're looking at how many cycles are happening in a second. So that's why we have that unit of seconds. Okay. Any questions at all on that first page before we move on? Okay. Number 4 that says at-home microwaves used in kitchens typically operate at a frequency of 2.45 gigahertz. What is the approximate wavelength in centimeters? So what do we think our answer choice should be here? Good, it's going to be D, 12.21 centimeters, right? So again, we're using C equals lambda nu, right? So convert 2.45 gigahertz into hertz, right? Then once you have that, you just plug into your equation. So speed of light is equal to, let's see, we're looking for wavelength, so it's wavelength times the frequency in hertz, right? So what's this frequency in hertz? Good, 2.45 times 10 to the 9 hertz. Okay, you solve for wavelength, you divide both sides. Guess that one doesn't like me. Okay, anyways, we divide by the frequency, right? So 2.45 times 10 to the 9. So you get lambda, and you might have gotten 0.122, which is good, right? But remember lambda, it works out that it's in the SI unit, so it's in meters. I want in centimeters. So how do you do that? There's 10 to the negative 2 meters in 1 centimeter, and then you'll get 12.21. Whatever, 12.2, 12.21. Okay, questions on that? There. Okay. So number 5, what is the energy of a photon of visible blue light with a wavelength of 470 nanometers? Okay, what are we thinking here? What equation do we have to use? So remember, there's two energy equations, right? What's one of them? Hc, who knows what goes on the denominator? Lambda. This thing like writes like an inch away from where I'm writing it. Lambda, what's the other one you can use? H times nu, right? So you choose which one you use based off the information you're given, right? We have a wavelength, so we're going to use the one that has wavelength, right? So, of course, again, you need to convert nanometers into meters. So when you do that, it's 4.7 times 10 to the negative 7 meters. Then we plug in, so E is H times C. So H, remember, is Planck's constant. So 6.626 times 10 to the negative 34 joules times seconds times C, which is the speed of light, which is meter per second. And you divide that by your wavelength, 4.7 times 10 to the negative 7 meters. So what do we get for the energy here? Good. So you get about 4.23 times 10 to the negative 19, and it's joules, right? It's joules because we're talking about energy, right? Energy is measured in joules, but you can also just look at the units in the problem, right? You look at my equation, meters cancel out, seconds cancel out, you're only left with joules. So that's how you get joules to work out. questions on number 5? Okay. Okay, number 6. Work on both of these. So I want to know, what is the energy per mole in kilojoules of photons of light with an emitted frequency of 6.39 times 10 to the 13 hertz? And then 7 is just choosing the statement that is correct. So take a couple of minutes to look through that if you haven't done it already, and then we'll go over it in a minute. If anyone came in late, did not scan the QR code for the attendance, can you please just do it on paper? Okay. Pass it around. All right. So what are we thinking here for number 6? What is going to be our answer choice? Good. It should be C. So you should have 2.55 times 10 to the 1 kilojoules per mole. So which energy equation was used here? Good. Planck's constant times the frequency, right? So energy is 6.626 times 10 to the negative 34 times the frequency, and I was very nice here and I gave it to you in hertz already. So you can just plug that in straight up. 6.39 to the power of positive 13. So what do you get for the energy when you do this? Good. So you get 4.23 times 10 to the negative 20, and it's joules, right? However, I am asking for the energy per mole and specifically in kilojoules. So from here, getting the energy per mole, we know we just multiply by Avogadro's number, right? Because 1 mole will have Avogadro's number of photons, right? So when you do that, I'm gonna write that down here, you will get, it's a pretty big number, it's 2547.3.06 joule per mole. But then I want kilojoule per mole. So we know we just divide that by 1,000, right? So when you do that, you will get answer choice C. Okay. All right, number 7, choose which of the following statements are incorrect. So statement 1 says radio waves travel faster than gamma rays. Statement 2, frequency and energy are directly proportional. Or statement 3, infrared rays are longer than microwaves. So what do we think is incorrect? Which answer choice? It should be C. So 1 and 3 are incorrect. Right? Number 1, you know, is total BS because all electromagnetic radiation travels at the speed of light, right? So none is, you know, radio waves aren't faster. And we know that infrared rays are shorter than microwaves, right? Okay, any questions on 7 there? All right. Number 8, so here I give you a Bohr energy diagram. Thank you. Anybody else need this? Attendance? You guys just pass that back, please. Thanks. All right, so we have a Bohr energy diagram, okay? I want to emphasize it is a energy diagram. So what could you imagine these arrows are representing? Energy, right? So this problem has multiple parts to it. So I want to know which transition arrow represents the highest frequency emitted, which represents the longest wavelength, which represents the lowest energy, and then which represents the absorption of light. So if you did not do this one yet, I want to give you a moment to think about it. You can discuss it with the people next to you. And a hint to this is you need to know these arrows represent energy, right? So to answer the following questions, you need to be able to recognize what the relationships are between energy, wavelength, and frequency. Okay. And also, I label these arrows A through E, so you can just answer like arrow A or whatever, okay? Anyone just coming in now, please make sure you do sign the attendance on paper. So just name and Z number, please. Please and thank you. All right, are we good to go through this? So for part A, we can do the answers first and I'll explain. So for part A, which transition arrow is representing the highest frequency emitted? We think B, you say? So let's see, we think energy, arrow B. Anybody have anything else? It's going to be E. Good. This is E. Which represents the longest wavelength? That should be B. And then for part C, which represents the lowest energy? That's going to be arrow B. And then D, which transition represents the absorption of light? A. So let's go ahead and reason those through, right? So like I said at the beginning, you need to first know that this is a Bohr energy diagram. So these arrows are representing energy. And then from there, you can use your knowledge about the relationships between energy, frequency, and wavelength, right? So, what is the highest frequency emitted? So in terms of emission versus absorption, right? When an atom is absorbing energy or emitting energy, how is the electron moving in terms of energy level? So for absorption and for emission. So if an atom absorbs energy, how does the electron move in energy level? It's going to go up in energy level, right? So up in energy level. And if it's going to be, if we're emitting light, if we're emitting energy, we're going down in energy level, right? So this is what this is telling you here, right? Remember n, the principal quantum number? This is telling you like where you're at. So the n equals 2, this is what we call the ground state. So it's the lowest energy. You need to know that the lowest energy, the ground state, is the most stable. Okay? So that's why like things all the time, like right, we have lights on in here. This is why things emit light, right? Um, the electrons do not like to be excited to higher energy levels. So when that happens, they immediately want to go back down to that ground stable state. Okay? So if we're looking at what is emitting the highest frequency, and every semester I forget to blank this out, but we're only looking at what is being emitted. So we're going from a high energy to a lower energy level, right? So we're only going to be considering these 4 arrows, right? Now, knowing that these are representing energy, right? What do we know is the relationship between energy and frequency? They're directly proportional, right? So that means the highest energy, the longest arrow being emitted is going to be the highest frequency. So that's why highest frequency emitted is going to be E. Okay. I'm not going to scroll just because it's going to move this thing. So for part B says, what represents the longest wavelength? So what's the relation between energy and wavelength? They're inverse, right? And even if you don't know that, you can reason it through by looking at the math, right? We know energy is hc over lambda, with lambda wavelength on the denominator, with energy technically on the numerator. They're going to be opposites of each other. So for answer B, for part B, sorry, if I'm looking for what the longest wavelength is, we know they're opposites. So the longest wavelength is going to be the smallest energy. So part B is the shortest arrow, smallest energy, so it'll be the longest wavelength. Okay, then for part C, what represents the lowest energy? Just the smallest arrow. I think that one is a little more self-explanatory. And then part D, what represents the absorption of light? There's only one. It literally says it on the paper, right? We have one going up. So that's why A is the answer for part D. Okay, does that make sense? Any questions about the Bohr energy diagram? Yeah, always. So absorption is always going up. Emission is always down. Okay. All right, moving on to page 4, we need to remember our quantum numbers. Okay, so remember we have 4 quantum numbers, right? So you need to know what the name of the quantum number is, what letter is associated, what letter is associated with it, as well as the rules to the possible values and what those limitations are. Okay, and you also just have to know like the definition of what that quantum number is telling you. Okay, so starting with the first one, we have the principal quantum number, which is letter n. This is just the energy shell around the atom. So the principal quantum number essentially is telling you the distance you are away from the nucleus, right? Because you could imagine if something has more energy shells, it's going to be further away from the nucleus, right? So actually, I didn't write it in here, but what are the possible values for the principal quantum number? Who can tell me that? Good. So n can go from 1 up until infinity. On the periodic table, we only see it go up to number 7, right? Remember, the period number on the periodic table tells you the principal quantum number. So we know n can never be 0 and it can never be negative. right? Because if it's 0, then like there's no energy level at all. So like that doesn't even make sense, right? So just know that it's 1 to infinity. The energy shell around the atom, right? So you have like your nucleus in the middle. The energy shell is like that, that probable location of where the electrons are orbiting, right? All right, the next quantum number is the azimuthal or the angular quantum number. So it goes by either or of these names. And the angular quantum number is denoted by the letter L. So we usually use like this script L. So the angular quantum number is describing the shape of the subshell, right? So remember our shapes. We have S, P, D, and F subshells, right? And they all have their own respective shapes, right? So the rule for the possible, the limitations to the numbers is that the L quantum number can go up to a maximum of n minus 1. So you see the L quantum number, the angular number, is directly contingent on the principal quantum number, right? They're all building on each other. Okay. Now, so everybody good so far? Any questions yet? Okay. So in terms of the shape of our subshells, right? Remember we have S, P, D, and F. You must know what L value is associated with each. So what is the L value for an S subshell? 0. What about P? 1. D is 2. F is 3. Okay. Any questions yet? All right, then our third quantum number is the magnetic quantum number. This goes more into depth about the subshell. So what the m sub L is telling you, it's telling you the possible orientations of these subshells. So right, we know these all have their own shape, right? So what I mean by orientation is imagine you took an s orbital or a p orbital and you threw it onto a graph. The way it can orient itself is telling you those orientation values. So you need to know that the possible orientation values, you can get it from doing negative L to 0 to positive L. Or what else can you use to figure that out? Good. You can also use 2 times L plus 1. Right? So why does this matter? It explains the number of orbitals that these subshells get, right? So let's take the p subshell, for example, right? Let's figure out how many orientations we have, right? So we know that when we are writing electron configurations, how many boxes does the p get? 3, right? Why does it get those 3 dashes? Do we just like for fun? Or no, there's a mathematical reason why. And that's because of the magnetic number. These orientations, this is the m sub L, right? So how do we get 3 for the p? We can do it by this way first. So from negative L to 0 to positive L. So if we're going to use p, for example, what's negative L to positive L? We have negative 1, 0, positive 1, right? We have 3 digits, 1, 2, 3. That means we have 3 orientations. Okay. You can also get that by doing this equation. So if you do 2 times L plus 1, so again using the p, so 2 times 1 plus 1 is equal to 3. This means 3 orientations, right? Okay, any questions so far? And then finally, the fourth quantum number, which is the easiest one, is about the electron spin, right? So the last one is the magnetic spin number. So electrons have a natural and intrinsic spin. Okay, so what this says, the amps of S, electrons either spin up or they spin down. So if it's spin up, it's positive 1/2. If it is spin down, it's negative 1/2. Okay. Now, it's either or of these because there's no way that you can like look at an electron and be like, this guy's spinning up and that one is spinning down. There's no way you can do that, so it's either or. All right. So any questions here on the quantum numbers, what they mean, what the limitations to the possible values are? All right, so I'm going to give you a moment to look at number 9. Which of the following sets of quantum numbers are not allowed? And there are going to be 3 answers here. All right, so for number 9, what do we think our answers are going to be? A, C, and E. Good. So A, is not right because N cannot be 0, right? Look at C. So what's wrong with C? The amps of L, right? If the amps of L is from negative L to positive L, right? Positive 1 is not a possibility, right? Because 0 is just 0, right? And for E, what's wrong there? The spin, right? 3/2, not right, right? It's got to be either 1/2, obviously, plus or minus 1/2, right? Any questions on that one for number 9? Yeah, in the back. How can L be for B? How can L be 4? So for B, N is 6. If the rule for L is up to a maximum of N minus 1, N minus 1, 6 minus 1 is 5. So the highest L value I can have is 5. So I can have 5, I can have 4, 3, 2, 1, or 0. Okay, does that make sense? All right, cool. Yeah, so good question. So if you do that 2 times L, right, that's telling you overall the overall possibilities, right? So 2 times 0 plus 1 is 1. So there's one possibility, right? However, for the actual, so the value of 1 is okay, right? But this digit of 1 is not okay. So if I do the negative L to 0 to plus L, there's no positive 1 in there, right? So I did that on purpose because this tricks. I was surprised no one brought this up because this tricks people every single semester. But and I specifically wrote it here. The number of digits is okay, right? We can have one orientation because this means L, we have an S subshell, right? So remember the S is just a sphere, right? So if I throw that onto a graph, one sphere, right, doesn't matter the way it moves, it's the same, right? So here the digit is okay, but the value of it is not. So that's why C was an answer. Okay. Any other questions with number 9? So again, those answers were A, C, and E. Okay. Number 10 now. Which of these represents the p orbital? What do we think? B, good. So this is the s orbital, this is the p orbital, this is the d orbital, and this is the f orbital. So do make sure you are familiar with those shapes. Okay. All right. Number 11 says, explain why atomic radius increases going from right to left and going down with increasing period numbers going down the periodic table. So periodic table somewhat kind of looks like this, right? So what's the trend for increasing atomic radius? It increases going left, and it's increasing going down, right? For the most part, all of the other periodic trends like ionization energy, electron affinity, electronegativity, which is important to us, they mostly increase how? Going to the right and going up, right? So atomic radius is the one that's inverse to all the others. So let's first describe, so if we go to the right across the periodic table, right? Why is the atom size getting smaller going to the right? Any ideas? Yeah, so more protons, okay? You have more protons. What is increasing going to the right across the periodic table? So okay, that's true, but it has to do with the protons. There's another trend that had to do with protons. Yeah, so okay, we're getting there. They're more attracted. Why are they more attracted? If we have more protons, who remembers what this is? Anybody remember the name of that Z with the star? Remember, this is the effective nuclear charge. Right? So as you're going to the right across the periodic table, the atomic number is increasing. So that means we have more protons, right? If we have more protons, which are positive, right, it's going to more strongly attract those negative electrons outside, right? So because of that, we have more attraction, right? Like, think the left side, there's weak effective nuclear charge. So like the electrons like out here, right? Then as we go to the right, it increases. So there's more attraction, right? It's going to be pulled closer. That's why it's getting smaller, right? So atomic radius increases going from right to left because Z star, effective nuclear charge, is increasing going across. Okay, does that make some sense? Yeah. Yeah. Okay, so that explains why the atom size decreases going to the right or increases going to the left. But why is the atom size also increasing going down with, and here's your key word, with increasing period numbers? What did I say earlier the period number was? What does that tell you? The shells, right? So the period number is how many energy shells you have. right? And that's much more intuitive than the idea of the effective nuclear charge, right? If you have more shells, you're taking more space, right? Imagine like I'm standing here, right? I am like a normal sized person, but what if I put on 50 hoodies? I'm gonna get like super fat, right? Because you're taking up more space, right? So that's the idea of that. So any questions to number 11 there? Okay. All right, number 12, which subshell is typically filled after the 4s subshell according to the Aufbau principle? What do we think? Good, it's going to be D, 3D, right? That's because, remember the Aufbau principle? This means you're going from lower energy to higher energy, right? And remember the trick that I taught you guys, if you write out a configuration, well, let me write it and then explain. And if you get confused on this, I suggest you do this because this tells you the Aufbau energy filling order every time. So if you write out the configuration and if you draw diagonal arrows going across, it tells you the energy order, right? So we know we go 1s first, then we go 2s, 2p, 3s. We go 3p, and then watch here, 3p, 4s, what's next? Then we get 3d, right? So that's why it's D. Okay, questions on that? Yeah. Yeah, so there are, and so both are right. However, when you're like writing the electron configuration, you have to fill the 4s first. So we do it in energy filling order. But if you write the 3D before the 4s, that's also fine, but that's just writing it in integer order. So yeah, if you like, you can see both of them. So yeah, good shout there. Yeah, she won't do that. Yeah, because they're both right. So yeah, you wouldn't see that. All right. So number 13, write the full SPDF notation for the following. So time is going by fast. Who has the configuration for magnesium here? Anyone? Yeah, what do you got? Good, you get 1s2, 2s2, 2p6, and then 3s2. Right? For nitrogen, you should have 1s2, 2s2, 2p3, right? And then watch for sodium here, right? We have a +1 cation. So we're going to have one less electron than what would be expected from the neutral configuration of sodium, right? So who knows what it's going to be for the sodium ion here? Good, 2p6. So you're just going to take away that 3s1, right? Because it loses that electron. Okay. Any questions about writing SPDF notation? Okay. Tungsten, which is element W, is used in some electronics, and it's actually used in a lot of lights, like modern lights now. What block of the periodic table is it located in? It's the D block, right? It's a transition metal, so it's part of the D block, right? Remember the periodic table? So your main group, right? This is the S block, P block, D block, F block, right? So what the block tells you is where, in what subshell the electron configuration is going to terminate in, right? Remember that? Questions on number 14 there? All right, number 15. Which of the following statements about core electrons is true? If you didn't answer this one, I'll give you a minute to think about it, and I'll ask for an answer in just a second. No, there's only one answer. And this is not the first time you've seen this question before. It's been in a past exam review. So what do we think is the answer here? So what is correct about core electrons? It's going to be B, good. So core electrons will shield outer or the valence electrons from the effective nuclear charge. Okay. So I think the analogy I used for this was imagine like two people are standing here, right? And imagine, so one person has a hose in their hand and they're spraying someone with a hose, right? They're gonna get soaked with that hose, right? But so think of the water from the hose like the effective nuclear charge, right? If one person is getting soaked with this water, right, and I stand in the middle between the hose and the person getting wet, I am like a core electron, right? I'm shielding the outer electron from that charge, right, from that water. So you can think of it that way. All right. Any questions about core electrons? All right. Number 16 says to draw the full orbital box diagram for sulfur. So you look at the periodic table for sulfur, right? You have to figure out how many electrons it has, which I believe is 14. And then you're going to look at where it terminates in the periodic table, right? So you'll see it's going to end in 3p, right? It's in the third period and it's in the p block. So we can write out our orbitals first. And I know to stop writing at 3p because that's where it's going to end, right? So sulfur, I believe it's number 14. I didn't write it here, but 16. Okay, so we're going to put in 16 electrons then, right? Yeah, I have 16 here, right? So how do we do it? We go 1s2, 2s2, then we move to the 2p, right? Now, how do we fill electrons when we have degenerate orbitals? So remember, degenerate, what does that mean? This means the same energy level, right? So can we, when we have degenerate orbitals, right, here we have 3 degenerate orbitals, can I fill in those electrons any which way I want? No, I have to do them one at a time before you pair them up, right? And remember, that was Hund's rule, right? So we go 2p1, 2, 3, 4, 5, 6. Right? Then we go to 3s, 3s2, and then it has 4 electrons in the p, right? So we go 1, 2, 3, and 4. So you add up those electrons, those arrows, and you have a total of 16 electrons. Okay, questions about that? I think that's hopefully not too bad. Okay, for number 17, what is the ground state electron configuration for molybdenum? I heard C, I heard D. What does everybody else think? Raise your hand if you think it's C. Raise your hand if you think it's D. It's D. Okay, remember, molybdenum is one of those weird ones in which it is an exception to the electron filling, right? So if you look at the periodic table, right, you would expect it to be answer C, right? Because it's in the D block, it's 4 spaces over, right? But because molybdenum is an exception, one of the 5 exceptions that you know that it's going to lose 1 electron from the S, and that 1 electron will go and migrate to the D, right? So this is just all due to its thermodynamic stability. And you know that some elements like to have a half-filled D, why am I erasing this? Half-filled D subshell. Some want to have a fully filled D subshell. So who remembers what these 5 exceptions were? So yeah, copper is one. Obviously, we know molybdenum is one. Chromium is one as well. Good. 2 more. Silver. It's another one. It's really expensive. Gold. Right? So copper, silver, and gold are, if you look at the periodic table, they're in D9. So these want a fully filled D subshell. So these want to have D10. Molybdenum and chromium are 4 spots over. So, right, 4 is really close to 5. So these want to have a half filled D subshell. So it's going to be D5, like we're seeing here with molybdenum. All right, any questions on those exceptions? So make sure you know those, all right? For 18, hopefully this is a very easy one. How many core electrons does an atom of nitrogen have? Should be 2, right? So remember, we have core electrons, we have valence electrons. If we have neutral nitrogen, which has 7 total electrons, it has 5 valence electrons. That means the rest have to be core, right? So that's it. Questions? I think we're okay with that. Hopefully it's like a freebie on the exam when you see it. Okay, so now for number 19, let's remind ourselves what the distinction between diamagnetic and paramagnetic is. So what does diamagnetic mean? Good, so we have all paired electrons. And what else does that mean? Repel what? So it's more, remember, it's repelled by a magnetic field, right? So like this is like more of an experimental repelled by magnetism. So if I take, an element of something that has all paired electrons, if it's diamagnetic, if I put it into a magnetic field, it's not going to be affected by that magnet. Okay? So what do we think paramagnetic means then? Good. So you'll have at least one or more unpaired electrons. This will be affected by magnetism. All right, so just make sure you were able to like look at, give me 1 second, look at an electron configuration and they'll ask like, is this diamagnetic? Is this paramagnetic? Okay, you have a question? Yeah, so like, um, I hate that, like I can't save this thing, but like, um, so the one that we did for sulfur, right? Like, I'm sorry, yeah, sulfur, right? We did that, right? In 3p, it had this, right? This is paramagnetic. So you could, it'll like show you that and it'll ask like, will this be affected by magnetism or not? Okay. All right. Next page here. Arrange fluorine, bromine, and chlorine in order of increasing first ionization energy. So I'll give you a moment to look at that. And you're going to have to use the periodic trend for ionization energy to answer this. All right, so what do we think our answer will be here? Should be E. All right, so I'm going from a low ionization energy to a high ionization energy. And remember the trend on the periodic table, it's increasing going left to right and from the bottom to the top. So you just find these elements on the periodic table and use the trend to answer. Okay, yeah. The trends, you mean? Yeah, so you have to know ionization energy, electronegativity, I guess radii, so the size, and I guess yeah, just those. Electron affinity, it also increases that way, but like you don't really, it's not really important. So yeah. Okay. So now for 21, for the following scenarios of difference in electronegativity, describe the nature of the bond. So remember this triangle in chemistry, this means a change in. And it also, when you get to like organic chem in a reaction, this also means heat. So if my difference in electronegativity is 0, what kind of a bond do we have? That is going to be purely covalent. If my difference in electronegativity is between 0.1 and 0.3, what kind of a bond do we have? Nonpolar. If my difference is between 0.4 and 1.7, it is polar. And if it is greater than 1.8, it's ionic. Okay, so absolutely you need to know the nature of the bond based off the range in electronegativity difference. Okay. So remember the nature of the bond, right? Polarity, that's just describing the relative symmetric or unsymmetric distribution of electrons, right? So we'll go into that a little bit in a bit. But yeah. So just make sure you memorize this. Okay, any questions on this here? All right. For number two, I give you three molecules, and you are tasked with determining both electron pair geometry and molecular geometry for the molecules. Right, so first here we have BeF2. So I need to know electron pair geometry and molecular geometry. So what do we think? Linear. Are they both linear? Yes, right, because the central atom does not have any lone pairs. So in this case, both electron pair and molecular geometry is going to be linear. Okay, and that's, of course, your Weissenberg chart that you have to memorize, right? It's got two electron groups, right? So it's a linear shape. And what is the angle between this bond here? 180 degrees. Good. Right, so make sure you remember you have to memorize all of the shapes of the Weissenberg chart. And in terms of the angles, all of the angles for the electron pair geometries, and then just those select two of the molecular geometries, right? Any questions with part A for BeF2? And is this structure okay for BeF2, even though the beryllium has 4 electrons? Yeah, right, because beryllium is an exception to the octet rule, right? So it can have an incomplete octet, right? Okay. Next, we have sulfur pentafluoride. So how does your Lewis structure look for this? Sulfur in the middle, and it's got 5 fluorines. Right? All the fluorines need an octet. Is this structure complete? There's a lone pair on the sulfur. Good. So for this molecule, what is the electron pair geometry? It's octahedral, right? It has 1, 2, 3, 4, 5, 6 electron groups. So 6 electron groups is octahedral. And what is the bond angle for octahedral? 90 degrees. 90 degrees. Okay. Now, will the molecular geometry be the same as the electron geometry? No, because we have a lone pair on that central atom. So what is the molecular geometry for this molecule? Good, it's going to be square pyramidal. Okay, and that bond angle you don't have to know. Yeah. Mm-hmm. It's got a negative charge, right? It's -1. Formal charge on the fluorines are all 0, but it's -1 on the sulfur. Okay. Um, okay, so what if I asked you on an exam, for SF5 minus, what if I was just very vague and I said, what's the shape of the molecule? So I don't specify electron geometry or molecular geometry. I just want to know what's the shape. What would you answer? Good. So when you're asking shape, it's always referring to molecular geometry, right? Remember that the electron pair geometry is an ideal geometry, right? But we know that once we have that presence of the lone pair, we're going to deviate away from that ideal geometry, right? Remember, we have electrons in these bonds and in this lone pair, right? And they're all negatively charged, right? And we know that negative charges will repel each other, right? So once you throw this lone pair on there, it's just pushing all these bonds out of its way, essentially. So that's why we're distorting the shape, okay? So if you're asking shape, you're always referring to molecular geometry. All right, what about Ni3 nitrogen triiodide? So like this. So what is my electron pair geometry? Tetrahedral. And what's the bond angle for a tetrahedral electron geometry? 109.5 degrees. And what is the molecular geometry? Good, this is trigonal pyramidal. And trigonal pyramidal, this is one of the two molecular geometry angles you must know. So what is the angle here? Good, 107.5. Okay. Yeah. So if it had two lone pairs, so like something like water, right? The electron geometry is tetrahedral, right? It's got two lone pairs, so what shape is that? It's bent, and we know it's 104.5. So these are just the two molecular geometry angles you need to know. But you need to know all of the angles for the electron geometries. Okay. And then, of course, you need to know all the shapes. All right. Yeah. Molecular. Yeah. Because again, this is ideal, right? But that lone pair deviates away from the ideal. So you always answer with molecular. Okay. Any other questions on determining shapes or angles? Okay. All right, next page. Determine the HSH bond angle in SH2. So you first have to draw the structure, right? So what do we think? C, right? So Maya, this kind of answers your question, right? I'm looking for the bond angle, right? Here the electron geometry is tetrahedral, right? But the molecular geometry is bent, so it's a 104.5 angle. All right. Questions with that one? All right. So 24, we propose these three resonance structures for the thiocyanate ion. Rank them in decreasing order of percent contribution to the hybrid model. So essentially what I'm asking for is what's most stable to what is least stable, right? Because we know that the most stable resonance structure will be the major contributor to that hybrid intermediate structure, whereas the least stable structure will be a very minor contributor to the hybrid. So I'll give you a minute to think about this if you haven't answered it already, and then we'll go over it in a couple of seconds. All right, so remember to look at what is most stable, and I kind of tell you here, we have to consider the formal charges, right? So let's start with structure A here. Okay, what's the formal charge on the sulfur here? -1. What is the charge on carbon? 0. What is the charge on nitrogen? 0. We go to structure B. The sulfur here has a formal charge of 0. Carbon has a formal charge of 0. And nitrogen, what's that formal charge? -1. Structure C, sulfur has a +1 formal charge, right? Carbon has a 0, and nitrogen has a -2. Right? Remember that formal charge is equal to the number of valence electrons minus the dots minus the sticks. Right? So what answer choice did y'all choose here? So this answer is going to be A. Okay, and this one is, actually, I meant to take this one off. This one's kind of tricky. So we know so to determine which structure is most stable, right, we follow the principle of electroneutrality, right? So that principle of electroneutrality tells you 3 things, right? It tells you you want to minimize formal charges, right? So right away, C. So let's just write that down. So principle of electroneutrality. So it tells you 3 things. You want to minimize your formal charges, right? So that's right. That's why right away C, is the worst and the least stable, right? Because this has 2 formal charges, whereas the other ones only have 1, right? Next, so this is why this problem is tricky. You want the negative charge on the most electronegative atom, and then you want a positive charge on the least electronegative atom. Okay? So a lot of people would say B, right? Because nitrogen is just slightly more electronegative than sulfur. However, this is more of an advanced topic, so this is why I think I was kind of mean with this problem. But electronegativity is not the full picture of it. So it also has to do with the atom size. So sulfur is a bigger atom, And in this case, sulfur would rather have the negative charge because it's bigger and it is better able to delocalize that negative charge. Okay? I know that's a lot of terminology, a lot of chemistry stuff, but for chemistry 1 purposes, the little trick is that nitrogen is obsessed with making 3 bonds. So if you see 3 bonds, you know this is going to be happy. So this is the best. This is second best. Can't even spell. Second best. And then we know this one is already the worst. So A is most stable, then it's B, then C is the least stable. Okay? Questions on 24? All right. Okay, number 25, consider the given molecule. What would we classify this molecule as? What do we think? D, this is a free radical, right? What tells you that this is a free radical? We have an unpaired electron, right? So I'm sure you guys have heard of free radicals before, or you guys have definitely heard of antioxidants before. So free radicals are terrible to your body. It causes so much damage. So free radicals are implicated in lots of diseases like cancer and a lot of like neurodegenerative diseases. So like Parkinson's, Alzheimer's. So last year I did research in Parkinson's disease, and there's one of the big contributors to that is the superoxide ion, which looks like this. So it's O2 minus. Notice that lone electron, right? So essentially this thing, it just, the whole idea behind it, right? This lone electron is not stable. Electrons like to be in pairs. They want to have a buddy with them, right? So free radicals, why they're so dangerous is that this one electron, it's going to look for anything around it to steal an electron from someone else, right? So I'm sure you can imagine if we're stealing an electron from something like DNA or like the cell membrane, it causes a whole bunch of damage, okay? If anyone here is a neuroscience major, you may learn about this. So yes, free radicals are dangerous, but this one to us, and hopefully to you guys right now, is actually beneficial. So this is actually used as a retrograde neurotransmitter, and this is used in synaptic strengthening when you learn and memorize things. So hopefully we're all producing some of this right now as we're learning, right? And then of course your body has its own ways to break this stuff down so you don't have too much of it. But unpaired electron, free radical, all right? All right. For 26, in molecules, as bond order increases, what is true? Say E. Good, it's going to be E. So as bond order increases, bond length will decrease, bond energy will increase. Right? So bond order, remember in a way, it's kind of, so remember the calculation for it. Bond order is the number of bonds divided by the equivalent shared atoms. So in a way, bond order is kind of like calculating the average number of bonds that a molecule has, right? So if we have more bonds, right, we know that single bonds are the longest and double bonds and triple bonds are shorter, right? So if we have more bonds, right? The bond length is going to decrease. And if my bond order is increasing, we're having, more average bonds, the bond energy will increase, right? Because we know that single bonds are weak and double and triple bonds are strong, right? And remember that analogy for bond energy, right? Think of them like they're pencils, right? If you have one pencil, it's really easy to snap it in half. But if I have three pencils, I can still snap them. It's going to take a lot more energy and more strength to break those, right? So you could think of those pencils like bonds, right? One bond versus double bond versus triple bond, right? And just for like exam purposes, I don't know if she went over this in class, but bond energy, there's another word we also use for it. It's also called bond dissociation enthalpy. Did she use that word enthalpy? No. So kind of. All right. So just no, it's so bond dissociation, right? Dissociating is breaking. All enthalpy means, you'll learn it in Chem 2, and we've used enthalpy, but we just didn't call it enthalpy. Enthalpy is the heat that you're providing to a reaction. That's all that is. Okay. So you'll hear all about enthalpy, which is delta H in Chem 2 when you get there next semester, hopefully. Right? Kidding. You guys are all going to pass this class. LOL. All right. Number 27. Which of the following molecules has a permanent net dipole moment? So we learned about polarity, right? But then remember that last day of chapter 8 where we learned that the geometry can affect the overall polarity of a molecule, right? So you can have, and so here's your hint, you can have polar bonds, but an overall non-polar molecule, right? Right? We remember that? Um, so which molecule do you think here has a permanent net dipole moment? So permanent net dipole moment, this is just saying what is polar. Okay, so if you don't have an answer, think about it for a minute so I can catch my breath and then we'll go over it. What was that? No, there's only one answer here. And a hint to answer this is you have to, unfortunately, you cannot be too lazy and you have to actually draw all the structures out. So while you think about it, I will do that to save us some time. This is so messy. So what do we think the answer should be here? It's going to be C. So C has a permanent net dipole moment, right? So what you need to consider is first whether the bond is polar or not, right? So from there, you would use that, what we did earlier, the difference in electronegativity value, right? So Ci4, carbon and iodine bond is polar, right? So we do have, and remember, we represent a polar bond with the dipole arrow, right? So remember, it always points to the most electronegative atom, right? So Ci4 has polar bonds, but because of the shape, it's overall nonpolar because we have dipole moments going in opposite directions with equal strength, right? So these vector arrows, right, they cancel each other out. Same thing with B, right? PF5, it's polar, but all in opposite directions with equal strength. So polar bond, but non-polar molecule overall. NCl3, this is polar, okay? Nitrogen and chlorine is polar, and a big giveaway here is this lone pair, right? So this is polar because I have no space on this thing. We know that NCl3 is a trigonal pyramidal shape, right? So if I, draw it in its real, like, shape, proper geometry, it's like this, right? So if it's polar, right, we have dipole moments. They're going down to the chlorine. It's not right. It's all going to the bottom. It's not canceling out, right? For DSO3, right, this is nonpolar because it's trigonal planar, right? So it actually, right, it's trigonal planar on a plane, right? So it's like that, right? So it's flat. It's equal, equal distribution, equal charge, equal and opposite strength, right? And then F2 we know is purely covalent, right? So any questions why the answer here is C? Yeah. Yeah, good question. Not really. It's all, yeah, no. Yeah, they're all going in opposite. They're all going away, so it's all canceling out, right? So remember this idea of polarity, right? Think of it like it's like a tug of war, right? The more electronegative side is going to win, right? It's stronger, it's going to pull those electrons towards itself. Okay, any other questions? Yeah. No. So those 5 elements you have to know, right? So remember, going from high to low, fluorine is 4, oxygen is 3.5, nitrogen and chlorine are 3. So sorry, there's 6 of them. Then carbon is 2.5, hydrogen is 2.2. Yeah. Sorry, yeah, I'll work on 28 and I'll write them because we are getting kind of short on time. So look at 28 super quick. All right, so those 6 numbers you have to know are up there. So for 28, we need to figure out hybridization. And for time purposes, I'm going to not draw the lone pairs. So for carbon tetrachloride, what is the hybridization of the carbon? sp3, right? Remember my trick for that? You count the electron groups. 1, 2, 3, 4. 4 minus 1 is 3, sp3, right? For CO2, what's the hybridization there? It's just sp, right? So same idea. 2 electron groups, 2 minus 1 is 1, and it's just sp. Okay. All right. All right, 29, the central atom of a given structure has, this should have an S, it has 2 bonds and 2 lone pairs. What's the hybridization? sp3, right? 4 electron groups, 4 minus 1, sp3. Okay. All right. Number 30 says to count the number of sigma and pi bonds here in the nicotine molecule. So we want to count sigma and pi. All right, so how many sigma bonds does this molecule have? 27. How many pi bonds do we have? 3. Right, so remember, sigma bonds is, well, so the next one just, goes more to depth with what they are, but in terms of counting them, every type of bond is a sigma bond. The only time you have pi bonds is with double and triple bonds, right? So you just count up all the bonds, you'll get 27, and then for pi, you just look at 1 pi, 2 pi, 3 pi. All right, and my suggestion is as you do this, even like on my answer key, I have a bunch of little hash marks because it's really easy to miscount these. I do it all the time. So you just count to make sure you don't count anything twice, make sure you don't forget anything. Okay? So any questions on sigma bonds, pi bonds, counting them? Yep. Triple bond, so it has 1 sigma and then the rest are pi, so 2 pi. Okay. Bro. Okay, so on the idea of sigma bonds and pi bonds, you need to know where those electron densities are found. So where would I find sigma bond? So here is a carbon bonded to a carbon, okay? Where do we find sigma bonds? So in the middle or is it outside? The middle. So here is sigma, okay? Remember, a sigma bond is when the electron density lies between the axis of the nuclei, right? So it's directly between this axis here. Okay, remember pi bonds are leftover and unhybridized p orbitals, right? So pi is leftover, that's an R, leftover unhybridized p orbital. Okay, and the way that you can remember that is think at like your Thanksgiving dinner or Christmas dinner. You might have some leftover pi at the end of the night, right? So pi bond is the leftover and unhybridized p orbital. Okay. So the pi bond is found outside of that axis. So we find pi here and here. Okay, so do make sure you know that last year that was on the test and it threw a lot of people off. So just make sure you know where those are. Okay. Okay, moving right along. This thing stopped erasing on the circle. Okay. All right, number 32 says, which of the following processes is endothermic in nature? So remember, endothermic has a positive Q value. Good, it's going to be A. So the sublimation, so what's sublimation? Sublimation is going straight from solid to the gas phase. Okay, so sublimation is going to be endothermic, right? So what does that mean? That means that heat is going to be inputted to the system. Okay. Now the rest of these, B through D, these are all what? What kind of a process? These are exothermic. So Q negative. Okay, and the reason, the way you can think of that is think of how the molecules are moving, right? So anytime molecules move closer to each other, when they're coming together, it is exothermic. When they move away, it is endothermic, right? So think of it like this. Think if we've got two atoms, right? And imagine there are two people who like are worst enemies, they absolutely hate each other, right? When they come together, right? When they're coming together, all they're going to do is fight and argue and there's going to be like a lot of toxicity, right? So fighting and arguing, all that, that's bad, right? And bad things are negative, right? When molecules move away, when these two people who hate each other move away, there's no fighting, right? And that's good, and good things are positive. So that's endothermic, right? So if we're going from solid to gas, right? The molecules in a solid are very orderly and very, next to each other, whereas in a gas, they're all like far apart, right? So you're moving away. All right, so you can kind of think of that, if that helps, but I know we're running out of time. Okay, questions with 32 on endothermic versus exothermic processes. Okay. Number 33 here says to calculate the specific heat capacity of titanium if a 43.56 gram sample absorbs 476 joules of energy, resulting in an increase in temperature from 20 Celsius to 41 degrees Celsius. All right, so what equation do we have to use here? Good, we use Q equals MCAT. So I'm solving for the specific heat for C. So for Q, it absorbs 476. Is this endothermic or exothermic? Endothermic, it's absorbing, right? So the heat is going into the system. So we have to use that sign. So we have to say specifically it's plus 476 for Q. Okay, that's equal to the mass, which we have, so 43.56 times C, which we're solving for, so that's X. And what's delta T? 21, right? Final minus initial, 41 minus 20 is 21. So you do some math here. 476 is equal to 914.76x. Divide both sides here to solve for x. What do you get for x? Good, 0.52. And the units are joule, that's a J, jeez. Joule per gram times Kelvin. Okay, and just remember that specific heat is the minimum amount of energy required to raise the temperature of a 1 gram sample by 1 degree. Okay, yeah. No, because remember it's delta T, so the difference will be the same no matter if it's Celsius or Kelvin. Questions with 33 there? All right. 34 says that a bag of chips has a volume of 1.5 liters on a grounded airplane taxiing where the pressure is at 1 atmosphere. Later, when the airplane is at a much higher altitude, the cabin pressure is at 0.75 atmospheres. And then you notice that the bag has become inflated. What is the volume of gas in the bag? So you need to look at what information you're being provided with and what you need to solve for, right? From there, you can choose which of the gas laws is appropriate to use. So which gas law would we use here? Boyle's law, right? So Boyle's law is P1 times V1 equals P2 times V2. Okay. So P1 and V1 is my initial starting set of parameters, right? So my initial pressure is 1 atmosphere. My initial volume was 1.5 liters. Final pressure, when you're up in the sky, 0.75 atmospheres. And then the volume you solve for, that's x. So 1.5 equals 0.75 times 0.75x. We solve for x, which is the final volume, by dividing both sides by 0.75. What is the final volume you get? 2 liters. So that's why the bag expands. If you've ever been on a plane with a bag of chips, you've probably noticed that. And if you haven't, next time you fly, buy a bag of chips and trust me. All right. Questions on 34 there? All right, last one. The eye wall of a hurricane typically has pressure around 950 millimeters of mercury. What is this pressure expressed in units of atmospheres? So what do we think here? Yeah, it's B, right? So what's the conversion between millimeters of mercury and atmospheres that we need to know? 760, right? So 1 atmosphere is equal to 760 millimeters of mercury. Divide them and you will get 1.25 atmospheres. All right. So that is it for me. This is everything you need to know for the final. All right. Yeah. So good luck, everybody. All right. I'm sure you will all do great on Monday. All right. Don't forget 7 o'clock in person. You need a Scantron, a pencil, calculator. Yeah. So good luck. All right. I wish everybody the very best and everything. Also, one thing. For future, so what I've done is, so this is my last semester. I won't be teaching here anymore after the summer semester. So what I've done is for the midterm and both finals, I recorded them and I'm gonna post them on YouTube for like final. I guess for you guys, the midterm is already posted on there. And then if you guys have like friends taking the class in the future, this stuff will be on YouTube. So there's a camera back there. Hi, YouTube world. All right. So yeah, thank you guys for a great semester. It's been great to have you all. All right. And good luck. Oh, also, sorry, the sign-in sheet, if it's somewhere, just bring it up. If you did not sign it, can you please just do it before you go? Thank you very much. Thank you. So during summer, we teach, it's online. So it'll be on Zoom. Yeah. And then I'm graduating, so I won't be here anymore. Thank you. Yeah, let me just, it's off.